right, so let's go and get started. So tonight, Republicans and Democrats are each preparing for their own independent apocalypse, and we're in here talking about plate girders. Gotta love it, right? While the election results are going to be pouring in tonight, we're going to be talking about bridges, of course. Before we get into the notes, thought I'd go over a little bit of housekeeping. So you all have an assignment due today, which I was checking my email right before class, and most of you had already sent that in, so yay on that. As for housekeeping, though, next week, I'm not going to be lecturing. You are, right? Because your research presentation is next week. So remember, 10 minutes, just the, hey, here it is on your failure, what was going on, what happened, why it happened, and here we go. You all have already got it completed, right? And everything's good to go, right? It's been done for weeks. There you go. That's what I want to hear. All right, halfway through. Okay, let's see, what else? So, was anybody not here last week? Because I've got, oh yeah, that's right. Okay, so I've got a few handouts. Let's see. So this is the stuff that was passed out last time. We're missing a couple. Or I wonder if they're... there you go. They might be in line for a while. I voted on Saturday, and I had to wait for an hour. Was that anybody? Okay. Was everybody else here last week? There you go. Okay. You need one? Okay. There you go. All right. Okay. I have a couple other items that I need to pass out. I had homeworks to give out last time, and I'm going to be completely honest, I forgot. Although, other than you, nobody, they aren't here. So, alas. Again, everybody's, like I said, everybody's preparing for their own apocalypse tonight, right? With the election. So we'll take a break, and then I'm sure probably during the break I'll pull up the map and see what's going on. Okay, but right now it's time to talk about bridges. Now I have to be honest with you, it has been a busy week, and if you're looking at my PowerPoint theme, you're like, that's not the PowerPoint theme that he uses. Well, I usually try and convert everything to that same theme, and this week it just wasn't happening. So I'm using my old theme. So I converted all the references to the current edition of the spec, so hopefully everything's still up to date. But in the meantime, I slacked on this one.
Good thing Lee's not here.
Yeah. I never hear the end of it, right? Okay, so I've got a piece of the spec, and I've got this presentation, which I'm going to hand out. One thing I'll give you some bad news and some good news. So tonight we're going to be talking about shear, which, generally with shear tends to be a little bit more of a big deal the longer the bridge, okay? So if you're dealing with like a 150-foot bridge or a 160-foot bridge, that's simply supported, shear can be a big deal. Nudge, nudge, wink, wink to the folks in the back. And are there some nasty plug and chug equations? Yeah. But good news is that tonight, because the process is very rote and very repetitive, I've posted an Excel sheet on Blackboard that'll have everything for you. You're going to have to modify this for your own bridge and whatnot, but in the end, I think you'll find it's pretty straightforward. And plus, I think this is sort of an important topic to discuss and help you all out with as much as possible, because in my experience, shear tends to be something that engineers maybe get a little scared of, and it's something that engineers, in my estimation, tend to screw up from time to time. And to be perfectly honest, it's not that bad, really. It's a pretty nifty little design, and if you're smart about it, you can double up on some elements and get some really economical designs. All right. So I apologize again. The slides are black and white instead of my typical theme, but it just wasn't happening this week. There's a lot of equations, and you have to convert them one by one, and just didn't quite finish it. All right, so let's talk about shear. With girders in general, you know, I-shaped girders, the bending strength of those girders tends to come from the flanges. The shear strength tends to come from the web, okay? Now, one of the things about girders themselves, you know, I-beams, is that when we were looking at moment strength of the girder itself, we were looking at its buckling capacity, right? Whether or not the flange buckled, whether or not the whole thing buckled, etc. With shear in webs, it's the same story. We still have to consider buckling. The mechanics are a little different and the equations are a little different, but you're going to find some very striking similarities, okay? One of the quirky things about shear is that when we look at the behavior of a beam that's subjected to shear, what happens is this. If we've got an element in a girder that's subjected to shear, we start loading it. It reaches a point when it buckles. But the weird thing is that with most plate girders, we can load them past buckling. They can keep on taking load even after they've buckled, which is a really strange thing to happen if it's the first time you've heard of it. But because we're dealing with shear and the elements that are being loaded are so constrained, they can actually develop post-buckling capacity through a phenomenon that we call tension field action. And we'll talk about how that works and the math that goes into it. I'm not going to lie, the derivation that goes into tension field action is a little involved, but ultimately it all boils down to very nice plug-and-chug expressions, which I know engineers love. All right, sound good? Okay, so I want to go back to this. This is sort of a fundamental topic in a lot of my classes because I do a lot of discussion with steel, obviously. If you've had a course in mechanics of materials or steel design or anything like this, you know, stress analysis is great, but one of the things you have to do is assess that stress analysis against a given failure criterion, or if we're talking about metals, a yielding criterion, okay? Now, it's pretty simple if you've got a bar and you're taking that bar and yanking on it. When does it yield? When it hits the yield stress. Simple, right? But if you've got an element that's subjected to all sorts of different types of stresses and shear stresses and normal stresses all over the place, you have to have what we call a yield criterion, an equation that determines, based on all these different stresses, is the element good or has the element failed, okay? Now, for metals, we use what's called the von Mises criterion, named after Hubert von Mises, who came up with it, okay? And for ductile, homogeneous materials, it works pretty well, okay? Now, if we have an element that is subjected to pure shear, okay, so every other shear, stress component is zero other than a given shear stress, we find that that element yields not when the shear stress equals Fy, but when it equals Fy divided by the square root of 3. So if you plug and chug 1 over the square root of 3, it comes out to about 0.577, something like that. When I teach undergrad steel design on my first exam, I always like to put a little question. I say, why do we multiply all of the elements that are subjected to shear by 0.6? Why do we use 0.6? Why does that 0.6 pop up all over the place? And there's a very simple answer, and it's von Mises, okay? If you open up the steel manual and you find anything related to shear, whether it's the shear capacity of a beam or it's the bolt bearing capacity of a given connection, or block shear, it all boils back one way or another to this, okay? Now, the steel manual uses 0.6. The bridge spec decided, nah, we're going to be a little more accurate than that, and the bridge spec uses 0.58. So what I propose to you is that the yielding capacity or the plastic capacity of an element in shear, according to the bridge spec, is Fy times the area times 0.58. Everybody okay with that? Now, here's the thing, okay? Elements that are subjected to shear have the potential to experience buckling. Now, what I mean by that is this. So I've got here a little video of a girder undergoing a test. So to give you kind of an idea of what it is that you're seeing, here on the bottom, this is the bottom flange right there. That's the bottom flange. here, up there, there's the top flange. And this big panel that we're looking at is the web. Now this is a girder that's actually made out of stainless steel, but in the end it really doesn't matter if it's steel, stainless steel, aluminum. We're still talking about a ductile material. Okay? Now what's happening is the beam is supported right here. There's a support behind this little column. You can't quite see it. And it's being loaded right there. See that white and red sort of hatched mark right there? So what's happening is I'm taking this element and I'm shearing it, right? Now what we're paying attention to is this web. And what happens is if you apply that load, and you notice they've got this sort of time motion because you can see people moving like they're Barry Allen or something. There's a Flash reference, if anybody watches the Flash. He watches the Flash, he gets it. Okay, there we go. See, you can see them in the background. There they are. A bunch of speedsters. Okay, but if you notice what was happening as the test was progressing is the girder, or particularly the web, was starting to crinkle, right? Now, what's specifically happening is when you look at the stress field, you find that the web is experiencing a compressive stress along this direction from this bottom left to this upper right. It's experiencing compression, and things in compression like to buckle, right? So that's what's going on, okay? Now, what we will find with our particular types of designs is that even though that thing is buckled, in most cases we can continue to load it. And by continuing to load it, we develop a tensile field in this girder. Because while this direction is experiencing compression, in that direction, I'm yanking on it. And I can yank on steel all day long. Okay? So this is what's called a tension field, and we'll attack that later on. For now, I just want to go back to this buckling concept. All right? So let's consider the following beam. Okay, so it's a simply supported beam. It's subjected to a point load in the middle. Now, I've done this because I want to look at a beam that is subjected to constant shear. Okay, so a little bit on notation. You all should recognize this, D, right? I've been using D to represent the depth of the web this whole time. Well, D sub naught is going to be the width of a given panel. Okay. So you think I've got these stiffeners that are arresting that buckling across the section. So we're looking at this little panel here. Sound good? Now, we're ultimately going to consider the two cases of shear buckling, unstiffened webs and stiffened webs. Stiffened webs being ones with stiffeners there. And the main difference is that stiffeners are going to provide what we call a nodal line for buckling. And that's just a fancy way of saying that stiffeners sort of act like a brace for the web, okay? Now you think you've got a column, right, and you load that column and it wants to buckle. You can increase the capacity of that column by bracing it, right? That's what a stiffener does for the web, all right? You're bracing the web. You know, when you brace a column, what do you do to that column? You ultimately make its effective length shorter, right? When you take its effective length and make it shorter, its capacity goes up. Same thing's true with the web, all right? Now, ultimately, what we're talking about is a plate subjected to stress. Now, I've shown you this equation before, right? The buckling stress of a plate, you know, and you've seen the buckling stress of a beam or a column. And for a plate, I mean, we could derive it if we want, but then we get into plate analysis, and it starts to go outside the constraints of what we're talking about in this class. If you want to learn about plate analysis, take Engineering 670. We'll talk about it a little bit in there. All right? But for now, just take my word for it that the buckling stress for a plate, a two-dimensional element, is taken from the following equation. Now, K is kind of like your effective length factor, and for an element subjected to shear, it's calculated as follows. 5 plus 5 divided by the aspect ratio squared, that D naught over D. Okay? So we've got a panel aspect ratio, a D naught over D, and a web slenderness. And that's ultimately going to be what the capacity of the web in shear is going to be defined as. Okay, we'll deal with the panel aspect ratio later. For now, I just want to look at the web slenderness. Because the web slenderness is kind of like the column slenderness. You know, the more slender it is, the weaker it is. Make sense? Okay. Now, the way I'm going to formulate this is as follows. Okay, I'm going to go back to this equation. Remember this capacity of the web, to reach yielding, the 0.58 times the yield stress, I'm going to adjust that quantity by a constant C. And that'll give me the critical buckling capacity of the web. So this C term is essentially the buckling capacity of the web divided by the plastic capacity, which, since we're talking about the same area, is just the critical stress times the yield stress in shear, which is 0.58 Fy. Sound good? Should be pretty straightforward. Okay. Now, if I set that critical buckling stress, which I derived as, K pi squared E over this quantity squared, or this quantity on the denominator, if I set that equal to that critical yield stress, what I can do is I can determine, here's the elastic buckling limit, here's yielding. We can determine when does elastic buckling occur by just solving for C. C is that buckling stress divided by Fy. Go through and do all of the alphabet soup, the algebra, plug and chug, work it out. And we get that we have an elastic buckling constant of 1.57 times K, which is just that quantity there, times E, good old Young's modulus, divided by Fy times the quantity, or times the slenderness squared. Where are we getting 1.57? It's just collecting your 0.58 here, your 0.58 there, and then 1 minus Poisson's ratio squared, which is 0.3. Just go through and do the algebra, collect everything over onto one side. I think you'll find it's pretty straightforward. Everybody good? Okay. So we have two buckling coefficients, okay? This is what happens if we get elastic buckling. This is what happens if we get no buckling. If we get no buckling, we don't reduce the capacity at all, right? We have a buckling coefficient of 1. Make sense? Because, what is C? C is serving to reduce that full capacity to calculate a buckling capacity. Sound good? So if C is 1, we're not reducing it at all. All right? So we've got full plastic capacity, we've got elastic capacity. Is there an inelastic region? Well, answer is yes, there is an inelastic region. Remember when we did beams, we had full plastic, we had that linear LTB region, and then the elastic LTB region. Remember that? Is there an inelastic region? Yeah. Okay. Where does that come from? That comes from tests and from experiments and going through the data. And what ends up happening is that occurs right around at a proportional limit of about 80% of Fy. And that number, again, it comes from folks going down to the lab and thinking to themselves, well, it's a good day to go take some beams and break them or load them to failure. So they go down, they test a bunch of beams, and this is what they find. One particular paper, or one thing I want to mention, is this paper by Bosler, because he did a lot of very fundamental work in steel research, and a lot of the stuff that I talked about last week and the week before, and the stuff I'm talking about tonight, a lot of that is derived from his work. So he was real influential in this field. All right, so we determined based on experiments that inelastic buckling occurs at around 80% of that yield stress in shear. So if you notice where I'm determining this buckling coefficient, I've got this proportional limit times the elastic capacity, and it's funny how this 0.58 just sort of randomly pops up. That the 0.8, not the 0.58. The 0.8 just sort of randomly pops up. Where does that come from? Again, it comes from experiments. So I take these two terms, do all the algebra, rearrange everything, and solve for C. And if you look here, I've got a lot of terms that are constants. Pull all those out, calculate this, and I get the following. Everybody okay with this? All right. So this is an expression that calculates the shear buckling coefficient of a given web. And it's a function of the web slenderness, the material properties, what's E, what's Fy, and what have you, and that term K. So the equations may look a little nasty, but all in all, it really is just plug and chug. Everybody okay with that? Now, if you look here, it says page 6-154. If you go to your spec and you look at the top and you see 6-154, I'll even turn to it with you. And see this column of equations right here? That's all that is. And ultimately, it's pretty simple and it's pretty plug and chug. Sound good? All right. Now, going back to that test that we did before, or looking at that stainless steel girder, you know, we loaded it and it buckled, but the question is, can we load it past that? And the answer is yes, okay? It's really nifty in steel beams. You can load it, it can buckle, and then you can keep loading it if we're talking about a stiffened element in shear. And that phenomenon is called tension field action, okay? So if we have an element that's being loaded in constant shear like this, when it buckles, it does something like that. So here's the element, it buckles, it kind of does that. Those web elements lose their capacity to resist shear in that fashion, and they just sort of deform as follows. Now, let's go back to some basic mechanics. Moore's circle, okay? Ooh, that's bringing it back, right? Moore's circle. It's probably been a while since we talked about this, right? So Moore's circle, it's ironic. I teach mechanics of materials or mechanics of deformable bodies this semester, and I did this morning, talked about Moore's circle. So I have an element that's subjected to a stress state, and what Moore's circle allows us to do is rotate that stress state and get a new set of stresses. Now, an element that's under pure shear reaches its principal stresses at about 40, or at exactly 45 degrees. That's our principal orientation. What ends up happening is in one direction, you're experiencing tension. The other direction, you're experiencing compression. I mean, just go through your mechanics of materials textbook, set sigma x and sigma y equal to 0, and you'll find your principal orientation as follows. Now, what ends up happening is this, okay? So this is a test that was done at the University of Missouri. This was actually done by a guy I do a little bit of research with. Let me see if this is it gonna play? Oh, come on. Actually, let me hit enable editing. Maybe that'll work. Enable content. Yes. There we go. All right. This was done by a colleague of mine. A guy I do a little bit of research with. This was done at the University of Missouri, and he's now faculty at the University of Wyoming. And what he was trying to do is look at tension field action in hybrid girders, where you have different flange stresses. He wanted to see, can we get it? You know, can we achieve it? And yeah, we can. So that was the long and short of it. But he was doing a shear test on a series of sections. So if you look, you know, he's going to do a sort of a 360 view of the section. This is the element that's being tested, and he's got multiple actuators on it. So you can see here right there at the floor, he's got an actuator that's going to push up on it. You can see that right here, okay? And he's sort of walking around. This is the element that's being tested, the one that's got the light shined on it. You can see a whole host of strain gauges that are being placed on this, all right? So he's sort of going around. Let me see if I can skip past the panoramic a little bit. So you can see it's braced on the back end, and you can also see that other actuator loading it on the top. Everybody okay? All right. Now here he's got what are a series of what are called string pots. These are measuring the deflection as the web goes in and out at a series of locations, and then also, of course, a number of those strain gauges. Let's see. Okay. Now, here's during the test. So we're loading the girder, and you can see it goes, right? But it's not like the girder just falls down and explodes. Okay, there's a point when it kicks in and it starts resisting that load again. Because again, it has lost its capacity in this direction. But in this direction, oh, it can still accept load because steel loves to be yanked on. Okay, so it develops what's called a tension field. Okay, and he goes through and he really zooms in because he wants to, oh, now, what the heck? I hit pause and missed the dramatic moment. Now he zooms way in because he wants to look at the surface of the steel. Notice how there's a lot of sort of this stuff that's flaked off the steel. Notice how the steel is at a different color. Okay. What happens when steel yields is that it begins to experience a large amount of deformation. Right there at the surface, it flakes off. Okay, those are called Luder's bands. That's sort of the name of it. But it gives you a visual representation of what's yielded and what hasn't. Okay, if you look at a lot of like black and white photos of steel tests where they've tested steel and they've loaded it inelastically, like beam to column connections and whatnot. What they do during the lab test is they actually take the girder and they paint it with like essentially lye. It's like a white powdery substance, and they paint it with that. So when you look at the test specimen, it looks like it's been painted white. Well, it wasn't paint. It was this powdery lye substance. And the idea is once they load it and it starts to yield, that white stuff starts to flake off. So you can take a picture and you can see, there's where it yielded. So food for thought. So that's why. Okay. Now, what happens is you develop a tension field that looks something like this. So I load the girder and I can still start to accept load in that tension state. Make sense? All right. So I propose that the nominal capacity of an element in shear is a combination of its buckling strength plus whatever increase in capacity we get from the contribution of tension field action. Okay, now that tension field force is, we're going to have to explore that a little bit. It's going to take a little while, and the derivation may get a little nasty. I'm going to do my best to make it as painless as possible. All right? Okay, so if I'm looking at a single stress field, just a single field by itself, okay, and that's a big point to make, okay, just a single field by itself, okay, I propose that the force we get in that field is the stress times the area, all right? So the stress is sigma sub t. I don't know what that is yet. We'll get to that. The area is the width of that field times the thickness, which in this case is the thickness of the web. Sound good? All right. Now, if we're talking about the force in shear, we're really talking about the force that can be developed along one of those stiffeners. So really all I can care about is that vertical component. So I take that force and I adjust it by the sine, sine of theta. Okay? And that tells me the vertical force, the shear force that I can count on. All right? Sound good? All right. Now, a couple things to point out. And some of this stuff is pretty basic, but it's going to change our derivation up a little bit later. Okay. Now the flanges are doing work at the same time. They're having to resist the moment. Okay. So the flanges are contributing moment capacity to the girder. Okay. They also have very low vertical stiffness. In other words, the only place I can develop the tension field is along this this vertical stiffener. In other words, I've got a tension field going, from here to here, and a tension field going from here to here. I don't have really any tension fields developed along the flanges because they're doing enough work. They've got to resist all the bending moment. And, they don't have much stiffness this way. You ever been in a fab shop, just pick up a strip of steel by itself. It has about as much stiffness as a wet spaghetti noodle. It doesn't have much stiffness that way. Make sense? All right. Okay. So I'm going to do a little bit of trig based on those assumptions. I don't have an element or a stress field along here. I'm going to do a little bit of trig to see if I can get rid of some of these unknown terms. Now, I propose that if you do all the trig and do the geometry and you say, okay, if this is the web depth and this is the panel width, what is the width of that field S? Go through and do all the trig and do all the analysis, and you find it's d cosine theta minus d naught sine theta. You all can do all the calcs to kind of see that. Sound good? All right. So I'm going to take that definition for S, and I'm going to plug it into here. And that's sort of what I like, because I want to eliminate any term I don't know. Like I don't know what that sigma sub t is, but we're going to tack that here in a little bit. And I don't know what that S is. Well, now I do. Based on those reasonable assumptions of behavior, I can plug and chug. Sound good? Now, what we want to do is look at worst case scenarios. So I want to look at the maximum force I can develop in that stiffener. So you all are engineers. You know all about math. I'm going to break out the the C word, a little bit of calculus. I know you hear calculus and it just causes nightmares, right? Well, I want to determine that extreme shear effect that I can get in that stiffener, so that means taking a derivative. I'm taking a derivative with respect to that angle because I want to determine the worst angle or the worst angle or dimension for that stress field. Because as my angle changes, my stress field is going to change as well, sort of a worst case scenario. So the derivative with respect to theta, go through, you all are engineers and mathematicians, you can take derivatives all day long. So take the derivative with respect to theta, simplify, and there you go. Now, if I'm trying to determine what theta is, I can say, all right, let's take that derivative, set it equal to 0, solve for theta. So I have d naught cosine 2 theta minus d naught sine 2 theta equals 0. I can say, all right, let's determine the tangent of 2 theta, d over d naught, go through and calculate all, or how did I do that? Well, taking this, add it over here. So d cosine equals d sine, then sine over cosine is the tangent. Really what I'm talking about is something like this, to keep it simple. If I'm trying to solve for theta, I can say, well, heck, this is really just that right triangle. So do a little bit of trig. Based on that triangle, I can come up with new expressions for the sine and the cosine. Then I'm going to break out those trig identities that you haven't seen for about 10 years. Remember all those, sine squared plus the cosine squared and the half angle formulas and the stuff you're like, oh God, not that stuff. Come on. All that stuff. Breaking out all of that. So we've got sine of 2 theta, cosine of 2 theta, and then that sine squared is 1 minus the cosine of 2 theta over 2. Referring back to the simplification I made a little bit ago, do a little bit of substitution, a little bit of simplification. And while the equation looks like it got nastier, it really didn't, okay? In fact, it got a whole lot easier to deal with because now, look at this. I mean, look at what we had before, okay? All right, here was our equation before, and it thinks, well, that's easier to deal with. Not really, okay? It's based on an S that we didn't know, and it's based on an angle that we didn't know, It's also based on a sigma t that we didn't know, but we're going to handle that here in a second, okay? Now, this equation might look a little nastier, but look at it. It's a function of d, the web depth, that's a dimension, 60 inches, whatever it is, the web thickness, and d sum naught, however far your stiffeners are apart. So while the equation got a little nastier, it's now a function of stuff that we know. That's the whole point, okay? Make sense? All right. Now, okay, so we have an expression that is related to, that will tell us what is the tension field capacity that we're developing based on that stiffener. And that's what we get, okay? Everybody okay with that? Now, we've neglected something that's pretty important. And the big thing that we've neglected is the beam, okay? The beam itself. And what I mean by that is we've looked at developing, some capacity due to the development of a single tension field, okay? But we're sort of looking at this in a little bit of a binocularic fashion. We're saying here's the, we're looking at it with tunnel vision. Here's the panel. We're looking at its tension field capacity. We're not looking at anything else. This is a beam with shears and moments and all sorts of stuff going on. Taking into account the fact that the beam is developing its own shear capacity and moment capacity and whatnot, we need to take into account that beam behavior. What the heck is going on everywhere else, okay? Can we get a benefit from that? Well, the answer is, yeah, we actually can, okay? Now, what I'm going to do this is I'm going to cut myself out a little chunk of this beam, and I'm going to look at the equilibrium and see what I can come up with. So I'm going to sort of cut out a little chunk to look something like this, okay? So what do I got going on? Well, the first thing I've got this stress field, right? Stress field going on. Now, I've got a shear on either side. I propose that, well, that shear on either end's got to be half of whatever we've developed from the tension field along that stiffener. I think it's pretty reasonable. Now, look what's going on with the flange. I got a force in the flange, but I got a force plus a delta. Why is that? Because, think, shear and moment. The flanges are carrying the moment. And even though I got constant shear, I got a change in moment, right? Goes back to that fundamentals that you learned in structural analysis or mechanics of solids or whatever course you took where you first learned shear and moment diagrams. I propose that the same thing should technically be true for the web. The web's going to be carrying a little bit of bending force as well, but it's going to be pretty negligible considering what the heck's going on. We're talking about some pretty high shear regions here, so we'll neglect that. The last force worth mentioning is this piece of S that's actually a potential compressive force that's going to happen inside that stiffener. So we use a little bit of equilibrium. Our good friend, the sum of forces in the x direction has to equal 0. These cancel. The f sub f's cancel. I got delta ff going to the left. That has to be equilibrated by our tension field. I guess I should actually have that over there for sign convention, but that'll be all right. What is our field that we're developing? What's the tension field that we're developing? Well, it's the stress times the area, but we also have to take into account the trig because that's going to be split up into x and y components. So there we go. That change in flange force is just going to be developed from that tension field. Summing moments, if I sum moments, about let's say the center of the section, a lot of these are going to cancel. Like for instance, the web force. Got a web force going this way and a web force going that way. It cancels. I've got my stiffener force going right through that. It cancels. In fact, the really only component that generates moment is I've got this delta F here at a moment arm of d over 2, and I've got the flange force couple right here, Vf over 2 times that width d sub naught. Why did that matter? Because I'm setting these two equal to one another, and I'm solving for this. Okay? So what I wanted to get to was this, is that we've got sort of two expressions that we can use for tension field action. If we're looking at the tension field by itself, which is what we got before, we had this. The tension field plus that beam behavior, we get that. They're pretty similar, right? Pretty similar? Okay. The only thing left we have to solve for is that's sigma sub t. The maximum stress we can develop inside that little tension field. Okay. Now, everybody okay on this so far? Oh, okay. Now, don't worry if the mechanics are a little funky. This is a pretty simple process, and I think you'll see how this goes. It's really not that bad. Okay. Now, this is the behavior of the beam if all it can do is develop a tension field. If you can count on that beam bending action, you can get a little more capacity. This expression actually ends up being a little larger in magnitude than this one. Where's the dividing line between where this occurs? That came from a lot of research that was done out of Georgia Tech, and there's a pretty simple plug and chug expression. If this limit is met, you can count on that beam behavior. If not, you got to go with the straight tension field. Pretty straightforward. All right. The last thing we got to do is solve for that sigma sub t, and that comes from von Mises. Okay. Now, what I'm going to do is make this a little simple. We're going to go back to an element of pure shear, and we're going to assume that we got 45 degrees. Okay. Now, in pure shear, we've got one element that's experiencing tension, one element that's experiencing compression. Now, I propose we're talking about post-buckling capacity. Okay. So we've got tau critical going this way and that way. What we're trying to determine is what's that additional sigma sub t. So see what I got going over here on the left? I've got a principal stress like this that's tau critical plus that sigma sub t. Sigma sub 2, that's a compressive tau critical. Everybody okay with that? All right. So plug and chug into this little nifty expression, and I get this. This is what's called a yield surface. And if you look at this, this is really the equation of an ellipse. Looks something about like that. Okay? Now, ultimately what we're trying to do is we're looking at a region that's somewhere in here, because this would be pure tension, this would be pure shear. So really what I'm trying to do is capture the effect in this region. And I'm thinking, I'm an engineer, I don't like ellipses. Why don't I just do a straight line? So let's use a straight line fit, and that straight line fit is this equation down here. That's just a nice little y equals mx plus b for that little region. That's all we really care about. Plug and chug, I get a nice little expression for sigma sub t. It's Fy 1 minus c. Go back to the fact that our nominal capacity is the critical buckling stress plus whatever we can get from the tension field. Plug and chug, and that's what we get. Nice little plug and chug expressions. And if you go back to the spec, what was it, page 153 and 154? There you go. Nice, pretty little plug and chug expressions. Everybody okay? In terms of determining the capacity, here it is. This is all there is to it. Okay? So if you have an unstiffened web, no stiffeners at all, then everything I've been talking about is complete junk, and it's either shear yielding or shear buckling. That's it. But if you do have stiffeners, which is more often than not what you're going to need in a longer span design, you have to go through the process. If you have end panels, we're not allowed to use tension field action on the end panels, and I'll talk about what that means here in a second. Interior panels, it's a function of whether or not this limit is met. If it is, we're allowed to use that beam action formula. If not, just the straight tension field action. And there you go. Pretty plug and chug. All right. So let me look at this. Okay. So what do I mean by end panels versus interior panels? Here's a beam sitting on an abutment. Okay. So here's the top flange. Here's the bottom flange. There's the web. Okay. Now these plates going like this, these are the stiffeners that we're talking about. Okay. This is what I'm referring to as an end panel. Over here, we're talking about an interior panel. We're not allowed to use tension field action on an end panel because we're talking about some pretty high forces and post-buckling capacity. Just from an element of safety, we just say, let's not worry about that. Plus, keep in mind a couple things. All those derivations that we just did, we were looking at a typical panel on the inside. That's point one. And point two, in order to develop those tensile forces, we have to have a pretty strong anchor on either side. And here, well, there is no anchor. There's nothing going on. So we're not allowed to use tension field action in that end panel. All right? Now, if we are going to use stiffeners, we got a couple things we got to keep in mind. For an end panel, the maximum panel length is 1.5 times the depth. If we're looking inside, 3 times the depth. Sound good? Okay. Now, what we're going to do is this, okay? I want to look at the following example. This is not, let me be clear, we've been doing that same problem throughout the semester. This is not that problem, okay? This is a different beam. But there's a reason for that. This beam is a little more flimsy in shear. It needs a little more attention when it comes to stiffeners, and that's for a very specific reason, okay? Now here's the dimensions of the girder, the top flange, the web, and the bottom flange as shown. All right, sound good? Okay. Now, you can go through and do a series of analyses looking at DC1, DC2, DW, the live loads. Here's the results, okay? So here's all the data. So I can go through and do strength 1, all that, and get the factored shear. For what we care about, we're caring about strength 1. Just 1.25 DC, 1.5 DW, and 1.75 times the live load. Sound good? Now, a couple things to point out. We've already got a cross-frame layout for this girder, and we'll talk about that later. But it would be really nice if when we're placing our stiffeners, if we could put a stiffener at the same place that there's a cross frame. Because that's the nice thing about this. If we can double up and use the same element, not only to connect our cross frames, but also to serve as a stiffener, it saves money. You know, stiffeners they have to be welded in. That's time and money that we'd like to avoid. Sound good? Okay. All right. Now, the first thing that we're going to do is we're going to compute the plastic capacity of the web. So the web is 69 inches deep. It's a ½ inch thick. It's 50 KSI. The plastic capacity is 0.58 times 50 times 69 times this. Plug and chug comes out to just over 1,000 kips. All right, sound good? Now, what I'm going to do is this. I'm going to determine what is the buckling capacity of this web, assuming we didn't have any stiffeners on this thing at all. No tension fields, no stiffeners, no nothing, okay? Let's just assume what is the capacity of this web by itself. So essentially what I'm using is, let me go back. I'm looking at this. No stiffeners at all. In fact, this term K, I'm just going to take K to equal 5. No stiffeners. Let's just determine the raw capacity of that web by itself. Okay. So the raw capacity by itself, we're going to take K to equal 5. So here's what I'm looking at. Okay? Remember that three-part equation, right? So first thing I'm going to do is find these limits. Okay, so 1.12 square root of EK over FY, that comes out to about 60. 1.4 square root of EK over FY comes out to about 75. Now the web slenderness is 138, so we're way the heck over here, right? And if we're way the heck over here, here is our buckling capacity, 1.57 D over TW squared times the quantity EK over FY. K is 5, E is 29,000 KSI, FY is 50 KSI, and D over TW is 138. Plug and chug, and you get a buckling coefficient of about 0.24, 0.239. Sound good? So, the nominal capacity of that web in shear, assuming that there are no stiffeners at all, is about 240 kips. Everybody okay with that? 240 kips. Keep that number in your head. Now, I propose that anywhere that that number is larger than the factored shear, we don't need any stiffeners at all. We don't need them, right? So let's see what the factored shears are. So here are the shears from x equals 0 all the way across the span, and I got that just from the analysis, which you all have, we've done stuff like this before, so you all should be fine on that. The sheared dead loads, should be DC1, DC2, and all that. All right? So what I'm going to do is I'm only looking at this first beginning region, from the first abutment sort of towards the main part of the span. Now I go through and do our strength 1 load combo, and I get 1.25 DC plus 1.5 DW, da-da-da-da-da, and here's what we get. So look at this. The maximum shear that we're getting, right there at the support is like, what, 380, 390 kips, something like that. With no stiffeners, the web can only resist like 240. All right? So I propose everywhere here we got to have stiffeners. The web by itself just isn't strong enough. So from x equals 0, right there where the support is, I drive along the bridge and I hit, what, 314 inches? From right there at the beginning of the bridge, 314 inches out, I got to have stiffeners there. I don't need stiffeners past that, just in that region. Make sense? So this is an important thing to do when you're doing this analysis. The first thing you got to figure out is where in the heck do I even need to put stiffeners? Sound good? All right. Stiffener layout is iterative, and we're going to use Excel. What I'm going to do is this. It is 7:23. Why don't we take a little break, and when we come back, we will go through the stiffener layout process. And I think you're going to find pretty rote, pretty straightforward, and then we'll talk about sizing those stiffeners. So I give you the final answer. Here's the final answer. We'll talk about how we generate that. But the next thing I want to talk about after that is, how exactly do we size? How thick does that stiffener need to be? How wide does it need to be? Etc. It's pretty straightforward. It's pretty plug and chug, but I do want to go through it with you. All right, sound good? So when we come back, we'll talk about how do we get this. Everybody good? All right. So let's take a little break. Let's come back. We'll get together at, what, 7:24. Want to get together 7:40? Let's give it time. We're doing good on time.